Okay, then I would say we continue with the last block for this year. And as announced, we're going to look into capacity expansion model, where the capacities of the different components of the power system are no longer fixed, but variable, where investments in new components are a decision variable. Again, we're recording as always, and maybe as a first recap, what we've looked at so far, we've so far as only cost, we've taken into account this short-term marginal generation cost, which considered only things like fuel costs, operation maintenance costs, and perhaps some costs for CO2 emission certificates. But we didn't look at any cost of maintaining existing infrastructure or investing in new infrastructure. What we looked at so far was this merit order curve, where you stack up the marginal cost of the different generators onto each other. You have gas in red, relatively high up the curve, wind and solar as near zero marginal cost technologies on the left of the curve, and where you intersect with the demand curve, in this case, a vertical line for a fixed demand, you have the marginal market clearing price. And this merit order you basically do over different time periods, which means that in different, or maybe I should say that market clearing also determines which of the power plants operate. So everything here left of the demand vertical line would be operating, and that then translates for different time steps and different levels of load, here shown as black lines, into different energy mixes, depending on, for example, the availability of the renewables and the relation between existing available capacity and the total load. So you see here as the shaded colors here, already you can see some elements of a merit order here that, okay, you have the wind and solar, it's basically just operating when it's producing, but then you can see here in the regions where you have a high demand and low renewables availability, you would have kind of this implicit stacking where you start with the brown coal, with the nuclear, the biomass, the hard coal, and then kind of top up with the gas in the peak periods. And that depends on the cost structure of, or in this case, still just the marginal cost of the generators. And some bits here, you will have kind of the charging of the hydro storage as additional load, shown here as negative values, and then dispatch here around, for example, here around the solar dispatch in the mornings and evenings, where you have demand peaks. So this kind of also translates into different prices in different periods, shown here as the purple line, lower prices when you have high renewables availability, and then when you have the gas as high marginal cost technology setting the price, you will have the highest prices. So that's here, that's the left axis here. There's some things here that maybe are worth a note of caution, is that there's some unrealistic elements here, namely that we didn't consider any kind of ramping constraints of the conventional technologies here. So you will see here the nuclear coming in for 1 hour, which is not particularly realistic because there are some ramping constraints to be done. There's also constraints that you can do. You can do this in these models. PIPESA has support for that as well, but we didn't consider it so far. It can also involve like binary decisions, which is a bit more complex, where you have costs for starting up, and then you need kind of an indicator whether in that period you're starting up the power plant or shutting it down. So kind of these things like ramping, startup cost, shutdown cost, minimum and maximum run times of the different technologies, all things that can play a role here in this setting, but are just not considered in this example. You can look at different weeks where the renewable, so weeks, or here we would just kind of double the renewables capacity. You can see how then when you have all the renewables, you might have more periods where you have zero prices and maybe more kind of variation in the prices themselves. And what do you do with this? Well, a couple of things we already see from that, and you might look at aggregate statistics of that, like the electricity mix, the average price or the distribution of the prices. Or what's also quite common is to just look at the kind of revenue streams of each of the different assets in the system, which ultimately determine how profitable it is or how worthy, or what an investment in the technology would be worth. So you can calculate all that from the models. For the revenue, you could calculate the electricity a unit produced. So that's your decision variable, times the market price. That would be your market clearing price, the dual variable of the energy balance constraints. You can clearly calculate the cost. That's just the terms in the objective function associated with that component. And then your profit would just be kind of the difference between the two. So that would be fairly simple, but also very common analysis in these markets. Something else that you would often see is a calculation of the carbon intensity of the system. You could use this, for example, to determine how green your data center operates at a given point in time, for example. And this carbon intensity is typically given in units of grams per kilowatt hour or tons per megawatt hour, and can be aggregated on various different levels, starting from the generator level, where you would just take kind of the specific emissions of the unit divided by its efficiency, so that you could get kind of how much tons of CO2 a unit of electricity emits. And then you can aggregate that over the system at a given point in time, or as an average over the whole system of the whole time period and all the spatial regions in total. So I think I showed one of these examples at the beginning, this electricity maps. Maybe start with that, where you can basically look at live what the carbon intensity of the different market zones in the European system is. So you have here, again, Sweden, Norway, Italy split up into multiple zones, because these are the zones where the electricity is traded at. You can see how, currently we have in Germany 381 grams of CO2 equivalents per kilowatt hour. And then you can also relate that to the share of carbon-free or renewable electricity. And get that pretty much, for almost all of the regions in the world, except for a few. So and this kind of data is really used, for example, by data centers or anyone basically trying to assess in their sustainability reports or whatever to assess what the emissions of their electricity consumption is. What's a hot topic here is, for example, that you could try, for example, if you have some flexible load, you could try to operate your load in a way that it tries to minimize the carbon emissions by kind of putting the load in the periods where you have kind of the lowest carbon intensity of the system. So and this map already here shows that you have your electricity systems not on a country basis, but on the basis of or the zones in which electricity is traded. And for each one, you would, in principle, have something like a merit order, a demand curve, and a supply curve that would match. And here, Apex Spot market operator would give you kind of one price per region, and sometimes they would be the same if you don't have any congestion between them. So where kind of, for example, a gas generator in Germany could be price setting for the French system. And these kind of the trade between the different market zones, so between each of the different market zones, there are some constraints about how much you can trade, and that is linked to the physical capacities of the grid. It's a bit more complicated in reality, but in general, you have some form of transmission constraints between them incorporated into kind of into the market and how the different market zones are linked with one another. What these markets don't know about, and they're completely agnostic about them, is what happens in the network inside. It's not completely agnostic. There's some form of approximation about it, but in principle, it's a bit blind towards transmission constraints within the regions. So one big discussion is in Germany about splitting Germany. It's quite a big market zone, which some tension between north generation in the south and a bit of high load in the south. Same for UK, where you have a lot of wind generation in Scotland, and then load centers towards London and big London area or southern England in general, which have stirred these discussions about splitting market zones. And that all has to do with kind of these markets being, or the individual market zones being blind to transmission constraints within them. And how does, for example, Germany resolve these transmission constraints? So it could, for example, be that you get a market outcome at bidding zone level, which is not technically feasible because you have limits in the transmission system. So you could have a result where, I mean, it's an unrealistic result, but suppose there's all of the generation comes in at the border to Denmark in Germany, and all the load is in the south of Germany, in Bavaria or somewhere. Then the market doesn't know that there might be transmission constraint on the way to connect the generation with the load. It would still say this trade is feasible. It's all in the same market zone, so I don't care about that. So how that is resolved then is that in the region, after the market clears, on the day where it's kind of physically happens, so this is all kind of traded on the previous day until noon the previous day, you would have the transmission system operator stepping in and saying, okay, to make this technically feasible within the zone, we actually need to make some adjustments to the market outcome. We maybe need to ramp up some power plants in the south closer to the load and ramp down some of the renewable generation in the north to kind of to alleviate the transmission bottleneck. So the market outcomes that we have, they ignore the physical transmission limits within the bidding zones. And that means that the transmission network operators may step in to curtail the renewables. That's primarily wind at the moment, but prospectively it might also be true for utility scale solar. Or so-called redispatch of other power stations. So it could be ramping up or ramping down production of power plants so that kind of network bottlenecks are resolved. And I'll show a few illustrations in a moment. Generally, I mean, from a very theoretical, idealized point of view, you could say this is quite costly because, well, it would be optimal if we could directly incorporate that into the market. So I brought here this SiGrid network that we looked at in the previous session, and brought here 3 different settings, 3 different market setups. So the first one here on the very left-hand side, that would be a single bidding zone like today. So I allow now here all the different regions to trade electricity, build a merit order without considering any of the transmission bottlenecks first. In the middle case, I split Germany into half. So very naively, I think at the 51-degree, so the horizontal line somewhere in Germany. Doesn't really matter where it is. In the real world, you would look at where the transmission bottlenecks are and then cut the network along these lines. And in the right-hand side, you would have here locational marginal pricing, where each of the dots forms basically their own market zones, which is something that you see, for example, already implemented in the US or New Zealand. And then kind of the constraints between the different zones are already incorporated into the optimization problem. So maybe it's a bit hard to see here what the differences are, but you can see some if you look closely. So in this case here, on the left-hand side, you see very little fossil generation. You see here some of the nuclear power plants and hydropower plants in south, and a lot of wind generation in blue in the north. If you look at already the two bidding zone case, you can actually see in a lot less wind generation and a lot more fossil generation. For example, here the brown coal and the hard coal in the south. And the reason for that is that somewhere along this line here, the model can see the transmission bottleneck and already anticipates that it needs to take some actions to actually make make the model make the electricity system feasible, or the market outcome feasible, and can directly incorporate any bottlenecks along this line where we cut. And we'll see, okay, I actually can't transmit all the wind to the south. So actually in the lower market zone, I need to ramp up some of the fossil generation because I can't bring all the wind down. And then it gets just a little bit more extreme if you can cater for that actually kind of node by node. And this is the ideal case where all the transmission bottlenecks in the network are known to the market. So if I take just a different hour with low renewables, you maybe get a similar picture, but not that extreme. I picked this example here because it's an hour with particularly high wind generation. So you actually have a high amount of bottlenecks, and that creates a lot of difference in the market outcomes. If you look at a period at a region without a lot of, or at an hour without a lot of renewables, typically you wouldn't see that many bottlenecks, and then the market outcomes between these different setups are typically quite similar. So it's kind of an effect that is intensified as you bring in more renewables. And what happens basically if you have we split up the bidding zones, you get different prices for the different bidding zones. For example, here, if the black line is shown here for this kind of 10 days or so, kind of where you have one bidding zone. The dotted lines, basically the two prices in the two bidding zone example, where you get then a split of kind of maybe higher prices in the south and lower prices in the north. There have been quite a few analyses published last year on that, what the actual effects are. This is, of course, just an example. And then for the locational marginal pricing, for the nodal case on the right-hand side, you would get kind of one price per zone, and then you maybe have a range that sits somewhere between them. That basically means why do you have higher prices in the south? Well, you can't bring all the low marginal cost renewables to that region if you factor in the bottlenecks in the network. So that means in that region you have maybe more conventional generation at higher marginal cost and needing to step in, and that increases the clearing prices. So if you just look at that, you might get a chart like that. If you just implemented that in our optimization problem and would look at the marginal cost, we would say, oh, the single bidding zone that is cheaper, then the two zone is a bit more expensive, and the nodal would be most expensive. Is that a good representation of the costs? No, because there's some hidden costs there's some hidden cost. It's because only the nodal is really technically feasible. The other two, they might have transmission bottlenecks that we have to resolve retroactively after the market clears. And that also comes with a cost. So redispatching some power plant and curtailing some renewables, that comes at a cost, so that you actually have here maybe some extra component of costs that might actually turn the system around, because the nodal pricing scheme here could kind of optimize around the transmission bottlenecks internally, whereas the single bidding zone doesn't see that, and then you might take up suboptimal decisions or have to pay remunerations to the renewables in the single bidding zone case. So we really have here the problem that the single bidding zone appears, first of all, as lowest cost, but it really ignores intrazonal transmission constraints. It's not a fair comparison because the first solution and more or less the second solution is also not technically feasible yet. And you can see that here in the line loadings, where in the first two cases, you actually have lines, so line loading here, where in some periods it goes above 100%, meaning that after the day ahead clearing, you actually have some overloadings that need to be fixed retroactively by redispatch measures. So if you have a bottleneck here and you have flows from that point to that point, one way to resolve loading on the line in a very simplified example would be to reduce generation here and increase generation here. So you kind of have some form of virtual transmission by moving the generation, but then not using the line that much after all. Yes, there's a question. Yeah. It's a bit, it has to be modeled, so it can be done, but it's not really a built-in feature. So if you're interested, there's actually an example how to do the redispatch in Pipesa, but it's a bit layered. So you would build one model and you would get an output of that, and then build another model that kind of changes a few things, incorporates for example, incorporates the decisions you have at the redispatch. You kind of have some form of decisions already fixed from the day-ahead market, and then you have different forms of cost, different costs of ramping up, and you have costs of ramping down the generation as well. So I think if you go to examples and then redispatch, you can look at that. But it makes sense to it's a bit more complicated. It's maybe not the most beginner friendly, but if you want maybe after you've gone through the Pipesa examples first, then the other examples first, then you can go here. It's not that long, but it takes a bit of like thinking, I would say. Yeah. Good. So I mean, this is from a simulation, not necessarily from optimization. And we see that we have some overloadings that would need to be fixed. We only have these yellow bits here in the left two cases, not in the locational marginal pricing, because in this case we would have all of these transmission constraints already incorporated in the market. So by definition, we don't have any overloadings here. So what we would see as redispatch measures, and taking now only the single bidding zone case on the left-hand side. This is the market outcome we looked at already before, exactly the same image. And then you can see in the center and the right the redispatch measures, where you have some kind of ramp up measures, where you ramp up some of the fossil generation here, lignite and coal here, for example, and then ramp down some of the wind and a bit of solar generation here. I mean, again, this is just an example for 1 hour for a heavily outdated model, but it illustrates the point that you have kind of this effect that kind of single bidding zone doesn't see the transmission bottlenecks, so you have to do you have to kind of above the bottleneck, you have to ramp down, and then below the bottleneck, you have to ramp up generation to kind of lift the burden on the transmission lines. So, and if you do that, and that's just the schematic plot, you will actually see that as you tend to have higher costs for the single bidding zone because you're not co-optimizing everything together, but kind of do one thing, and then you might be locked in to some extent and need to pay compensation for changing decisions, infeasible decisions that you made in the single market zone. There's a big discussion about the nuances of bidding zone splits. This is not the point here. It's more about how can we model that eventually. But I can point you to some of the studies. There's been a big study about on the there's been a bidding zone review by the NSOE group of transmission system operators in Europe. There's also been an Agora Energiewende study that looked at these aspects in detail, and also there's a lot more arguments to should a bidding zone be split or not, that exceed the scope of this course. I pulled up also this from the Fraunhofer energy charts, a quick statistics about the time resolution of the time resolved redispatch over the month of November this year. The colors mean basically different market zones, different redispatch measures, and positive values here would be ramping up. We could see, for example, ramping up in the Transnet BW, so southwestern transmission system operator region, and a ramp down in the 50 hertz region. And here you have range of, so I think it's hourly resolved, so you have something like 1.5 gigawatt in some of the hours. Good. Okay, so that's one thing worth taking in mind, because it's one thing that most of the capacity expansion models, so the models that also look at investments into new technologies, into renewable technologies, into storage, typically assume that if you have a regionally resolved network model and allow investments, the underlying market scheme will most likely be a nodal pricing scheme, which is much more idealized than the market setup that we see today. So that's the main reason why I showed this. We're not going to model redispatch ourselves in the course, but it's an important caveat that when we do investment decisions in the models that we're going to use, we're always working implicitly with that case, where implicitly we have one market region per transmission node, rather than the status quo case of a single bidding zone in Germany. So what changes now from modeling electricity markets with existing capacities to the scope of system planning, investment planning, or capacity expansions? It's various different terms that you can see thrown around for the same type of problem. Well, so far we had in the optimization problems that as the decision variables or the degrees of freedom in the short-term perspective, the dispatch of the power plants, the operation of the storage units, or also the curtailment of the renewables. And we basically promote now the limits of these dispatch decisions to decision variables. So we can invest in new generation, which expand the scope for the dispatch of a power plant, or wind generator, or transmission line, or whatever component. Investments in generation, investments in new storage units, as well as investment in transmission reinforcements. And I'll show in a moment how that looks in the optimization problem. So we're taking now a more long-term perspective, where we'll optimize the investment in capacities for the different power system components and promote the limits to capacity expansion variables. We already did this a couple of times in this model.energy example at the very beginning of the course, where one of the decisions that this model here took was what should be the optimal mix of the optimal capacities of solar, wind, battery, and hydrogen storage. That was already a case where we had capacity expansion in a model. In terms of transmission grids, you will see that these types of models being used, for example, to figure out the value of different projects for transmission expansion in Europe, for example, in this TYNDP, 10-year network development plan in the NSOE, where you basically have a set of different projects at various planning stages that need to be evaluated on a European level. What they're basically, they do a cost-benefit analysis, kind of what would be the welfare in the system if this line is there, and what is it if the line is not there. And then based on the level of value, they can, the transmission system operators or the kind of project developers can apply for funding and subsidies for these projects, especially if they are of kind of cross-country interconnector basis. Just to kind of, yeah, interconnect the European grid better and deal with, I mean, comes with various advantages of integrating renewables more easily. So in terms of the optimization model, in terms of math, this is what you already know. This is kind of the optimization problem we had in one of the previous lectures, the energy balance and the generator limits, storage limits, storage consistency equations, and the line limits, as well as Kirchhoff voltage law, with the decision variables in red. And what we now have is we have a slightly expanded model that in principle doesn't change, but we have new investment decision variables in blue. These mostly kind of refer to the limits of the dispatch variables, and this is how kind of the decisions are linked. And we have a couple of new terms in the objective function as well, where we now, in addition to the operating cost, we are factoring in the investment costs in new technologies. So I think we need to talk about the objective function in a little bit more detail, because there's a couple of challenges that we need to resolve somehow, because we have kind of some costs that are more short-term, and we often look at a year of data, for example, and then we have here maybe some cost for all snapshots in a year, and the weighting here might be just the duration of a time step. So if this also protects you against kind of 2 hourly resolved models, but you have usually here some form of operating costs across a year versus investment costs for assets that typically last like 20, 30 years. So it's a bit of an unfair comparison. If you just look at the year, you would see that almost all of the components are not worth investing in because they can't recover their investment costs on the market in a single year. Might be true for some very good technologies in certain markets, but in general, you will have to make some assumptions about aligning your comparison frame of the operational cost versus the investment costs. And one common way to do that is to do everything based on an annual cost. So you have maybe 1 year of operational costs where your weights sum up to 760 hours, and you have some investment costs that you break down to an annual value. So if you have so in very simple terms, and we'll make it more complicated in a moment, if you have an asset that runs for 20 years, you maybe just divide the upfront investment costs by 20, and then you have a common reference frame, but that you have kind of total system cost in a year that you try to minimize. So this is kind of basically what this slide is about. You have different units here where kind of your weight aligns the euro per megawatt hour cost with the megawatt dispatch decisions, and the hour unit comes from the weighting of the snapshot. And then you have investment costs either in euros per megawatt or euros per megawatt hour. And then you kind of make sure that the red part and the blue part represent kind of our costs that represent the same time frame, so that you have a way to compare a technology that has maybe high variable cost but low upfront cost to technologies with low variable cost and high upfront costs. So the common way here would be to look at yearly system costs, where your weights sum up to 8,760, and your investments are so-called annualized investment costs. And annualized investment costs, and those who did either energy systems or energy economics, the annualization involves some notion of kind of time valuation of money, a so-called present value, where your value of cash flows of money over time has different value, whether you get 100 euros today or 100 euros in 10 years' time, due to inflation and interest rates and opportunity costs of different things that you can do with the money. You would most certainly prefer 100 euros today rather than 100 euros in 10 years' time. And people, when looking at cash flows over different years, need to kind of so-called discount that to account for the fact that kind of income later in 10 years or 5 years' time is worth less. So you bring everything based on the interest rate to a present value, which is then kind of lower, so lower than the nominal value far into the future. So future income or costs are just worth less than from today's point of view. And what you then have as a special case, for example, if you expect kind of for your asset a constant cash flow over T years, you calculate the so-called present value factor. So you say you have the same nominal income over T years. You want to look at, okay, what is that worth from today's perspective? And you kind of accumulate all of that. And for each of the years, so for each of the years, you discount separately. So this is kind of, you bring a series of equal payments, of equal annual payments to a present value. And the opposite concept of that would be exactly what we need. We have some upfront cost of an investment, and we need to distribute that over time into annual values. And this is just the opposite. The annuity factor is just 1 over the present value factor, which kind of takes an upfront investment cost and distributes that over equal annual values. And that is really, in principle, just like a mortgage on a house, a credit you pay back, where you have an upfront payment and then kind of, or upfront credit, and then you pay it back over the years. And that is a very common option to distribute your investments over annual values, and then you can compare these annual costs in investments to the annual costs of the operation, with the implicit assumption being that each year of operation would be the same over the lifetime of the project. So have a look at the equations. But a good rule of thumb is, for example, dividing the upfront investment costs by 10. That is true for most of the components. The specific annuity factor, it depends on what your interest rate is, or discount rate, and the period over which you pay it back. You can look at these tables, and many technologies have like maybe 8% discount rate and 20-year lifetime, and that's roughly a factor of 10. So kind of, yeah. So when we kind of look back into our objective function, we now have kind of made sure that the red and blue parts are aligned, that both sums, or both terms of the sum are in annual values. They share the same unit. And with that, we can continue. So far, I showed basically all the constraints that we have in the system are the same. There's a few additions that you would typically see in capacity expansion problems. You would see this. I'll get to that in a moment. But the more basic thing is that you would see for your investment variables, you would also see limits themselves. So the investment, the capacities limit the dispatch, but the capacities themselves might be limited by the land eligibility calculation that we did at some point. So kind of maybe it's limited how much wind you can build in a certain region. So the investment variables may not be unbounded, but they may be bounded on the upper level by kind of the eligible land area. Or also you could see it as you might have lower bounds because you already have a certain amount of this capacity in the system. And you would say, okay, you set this as a lower bound, and you always want to start with that. One thing that we already experimented with in the previous PIPESA example in the market section is that we maybe want to limit CO2 emissions. So we maybe want to bring, especially when we do capacity expansion, we want to nudge the system into investing into technologies that may not be cost optimal if you don't consider that there's a cost associated with the carbon emissions. I mean, we know for sure there's kind of high cost associated with carbon emissions, and there's clear strategy or consensus that this should be reduced. So when we look at kind of how could these future systems look like, kind of one of the key constraints would be adding this limit on the CO2 constraints, exactly the same as I mentioned last time. Basically calculate how much a unit of electricity of a certain carrier would emit in tons of CO2. You iterate that over the whole period that you're looking at, the whole regions, the whole different carriers, based on the specific emissions and the efficiency of the generator, and then limit that to some value. For example, 0. Could also be 0 if you want to look at a climate neutral system. And as I mentioned earlier, is that just checking if my audio is still running. Yes. So what we looked at earlier is that the nice thing is that the shadow price that you get out of this constraint, you can interpret as your CO2 price. That wouldn't be kind of necessary, would be the corresponding political target for achieving this level of CO2 reductions. Okay. Any questions so far? Because that settles the theory. I brought 2 more examples. Kind of one very basic example, and then kind of one study I did at some point that is maybe a bit critical of all this cost optimization. And this is one study that kind of Tom Brown did with a couple of other people before I started, or actually at the time roughly around the time I started modeling with PIPESA. But I think it's kind of a neat study because it's kind of you can still follow most of the things that are going on. Studies got more complicated over time, but here basically is kind of this study that tries to factor in or tries to calculate what the benefit of cooperation of building transmission lines between the different regions in Europe would be. And it starts with this kind of hypothetical case, which is not how it is in reality today, that all the different countries are isolated and have to get to 95% carbon reduction, and kind of the only fossil generator they have available is the gas. And then you have costs of like 86 euros per megawatt hour, certain fractions of battery, hydrogen storage, wind and solar. And then each of the countries must balance their load independently. And there you have kind of again in black the load, and then you have a kind of some variability from the wind that needs to be kind of counteracted with the hydrogen, or balanced with hydrogen storage, so that in sum your total generation matches the load. So far so good, nothing new compared to what we already talked about. But here you basically you have no option to trade electricity between the regions. So here you have some period where you have an excess of wind that cannot be put into storage because the storage sizing is not cost optimal to build more of that. Then you have some curtailment here. So if you allow the system to kind of optimize the capacities, you can achieve much lower costs, maybe 64 euros per megawatt hour. Again, it's all just illustrative. And how does this cost reduction come into place? Well, a couple of things happen here. So first of all, you need less storage capacities. So you have, again, this kind of competition between balancing renewables in space and with transmission networks and balancing renewables in time with storage. You have here an effect where the system prefers to integrate more wind into the system and can do so, kind of bring in more wind from the British Isles, for example, into Central Europe, which in this kind of setup back then had lower cost. So it would shift some of the investments from solar, which is available everywhere, to wind that is available just in a select few regions in Europe, at the additional cost of some extra transmission lines. And in total, you just contract the total cost. And the benefit of that kind of is due to the imports and exports in different periods, here shown for Great Britain, where you have Great Britain just exporting in the periods where it has an excess of renewables. It also, compared to the previous case, just builds much more wind, so we have much more frequently in case of excess. But on the other hand, it will also import from other regions at some other times. And this is something that we do very often, is that we play through different hypothetical cases, sometimes even interpolate between the different cases. What you see here on the x-axis is kind of how does the kind of a linear or a relationship between the level of transmission expansion between 0, the one example I showed, and cost optimal, the other example I showed. And then you can see often some non-linearities where you have some cost optimal trade-offs between expanding the grid and kind of the first few units give you a much higher benefit than the last few units to the cost optimal. So whether it's 200 or 250 terawatt kilometers, so that's just capacity multiplied by the length of the line, the difference here is much smaller than the first 50 units here. And that already shows you that one of the problems here is that, well, it's a difference of maybe 0.5%, and how accurate are our models actually? And isn't that just a bit of kind of model artifact that we end up here? Couldn't it have been much better here? And actually, it could have, from a practical point of view, maybe this is much better because it has kind of low cost increase, but kind of avoids some of the technologies, transmission expansion, where you have problems implementing that because of public acceptance. So there's more to these systems than cost optimality, and it's worthwhile knowing about kind of what are the trade-offs and how valuable the build-out of different technologies is, especially if it's critical that you'll see the technology development that you expect, or the public, or whether it will realize the public acceptance that you expect for that technology. This is where this paper comes into play. This is one of my PhD papers where we looked at so-called near-optimal systems, kind of trying to quantify what alternative solutions are there actually within kind of 1 or 2 or 3% of the cost optimum, and does that give us any interesting information about maybe solutions that are less dependent on certain technologies or more publicly acceptable? And yeah, I brought here this kind of illustration, but it kind of breaks it down into 2 dimensions. So the x would just be kind of your projection of all the decision variables in the model, including operational and dispatch decisions, and your objective function, f of x. And you would have something like this as a feasible space, kind of all the constraints that make it kind of infeasible to use this option or this option. But then you have always the kind of optimal solution kind of at one of the corners at the lowest point, but then it might be very flat around it. So it might be very different solutions within a small cost penalty on the optimal objective. So somewhat like this, where you maybe introduce a constraint that your cost f of x must be less than 1 plus epsilon, your optimal cost. That gives you a bandwidth of solutions, or kind of it cuts your solutions into a part that is near optimal. So solutions that are within epsilon% of the cost optimum. And then within that space, and it's up to you how do you define the epsilon, you might just even iterate over the epsilons. You can look for solutions that minimize or maximize certain features, certain decision variables, for example, the investment in wind or in transmission lines, that stay within the set budget, basically. So you basically change the objective for the new search direction, the thing that you want to minimize or maximize, and introduce a new constraint, the budget constraint, that kind of once you have a cost optimal solution, you will stay within kind of epsilon of that budget. So here's an example of that concretely. So in the left case, you have cost optimal transmission expansion across the European system. You can see quite a lot of transmission expansion, the generation really kind of at the periphery of Europe, where you would see the lowest levelized cost, the best resources for these technologies, the solar in the south, the wind across the North Sea. But then you can see that as we introduce a budget of, oh, you can't see, sorry about that, but I haven't figured out a way to remove the window there. But so this is, on the right-hand side, you can see an example of 5% extra budget, where we try to minimize the transmission volume. And you can already see for 5% extra cost, you can see a lot less transmission expansion. And what happens is that you can see some of the kind of wind and solar generation moving further inland, closer to where the demand is. And this is just one example. And you can iterate over different technologies, not just transmission, but maybe also wind, solar, different types of storage. And also you can iterate over different budgets and also about minimizing and maximizing. And what you get is basically something like Pareto fronts, a term known from multi-objective optimization, where you can define kind of a space of solutions that exist within a given budget. So what you can see here on the x-axis is the epsilon, so the extra budget that you give to this solution. And in this example, we look at the transmission system, and we have one Pareto front for minimizing from the optimum. So there's a shared point here for the optimum, and then we try to minimize as we go to higher allowed cost penalties. And we have the same concept for maximizing. And because our problems are convex, we can actually say that we can also find a solution, near optimal solutions in that shaded, green shaded space. And the nice thing here that you can see is that, again, you have some form of nonlinearity, that the kind of first units of cost penalty, they can change your transmission results drastically. So you could say, okay, transmission expansion is critical. It's seen critical by people. So if I allow the system to be 0.5% more expensive, I can actually reduce transmission expansion by 20 or 30%. And that's a very useful information for decision makers to know what the trade-offs are, and that they don't have to follow blindly the result of the cost optimization, because it might be very random where the cost optimization exactly ends up in, because we have some uncertainty in the models, some uncertainty in how accurate they are, what their resolution is, and also a lot of the parameters that we put in, like the cost assumptions, for example, are also uncertain. And that you can extend to all the different technologies. You can see kind of technologies that don't go all the way down to zero, up to a certain level of cost penalties of absolute cost budget increases, they could be seen as kind of, you definitely need to stay within 10% of the cost optimum. You definitely need to build that much amount of wind. For other technologies, you might have some substitutability. So you might be able to get away with no solar in an all electricity system model for kind of let's say 8%, and get rid of onshore wind for 4% extra cost, but maybe not both at the same time. These are completely independent runs. So if you go for low wind, for example, you would tend to see kind of it being compensated by high solar or some other low carbon generation technology. So what you can read from that is not only kind of how flexible is your choice, very close to the optimum, but also kind of what's your robust minimum constraint for the capacities. So you need, I mean, this is a couple of years old now, and only for an electricity system without kind of renewables, without heat pumps and electric vehicles and so on. But you could see that in principle, if you have a model that you trust, you could say, okay, I definitely want to stay within 10%. Well, then I need at least that amount of solar, and I cannot build more than that. Although I think the lower boundary is in many cases just more interesting. So the question is, what do we know what people accept? Do we accept 5%? Do we know 10%? Do we accept 20%? And there's been some studies by Evelina Trudnevete, one professor in the University of Geneva, for example, who kind of looked at retrospectively, kind of in the past, how far have the real decisions in the energy system, how far have they been from the cost optimum? And you end up with values kind of in the range of 20%. And with 20% changes in system cost, you can do a lot of things. And you can see it one way, that we have a high willingness to pay for suboptimal solutions and that other things than costs play a big role, or you could attribute that to just inefficiency in how the energy system was planned in the past. But it's good to have kind of some orientation value here of what we've been at least implicitly accepting in the past. And kind of that's it for today. We meet again in January, on the 8th of January. No lectures next week. We'll do capacity expansion in PIPESA, and then there will be the consultation hour for assignment 3. Until then, you have some time, I hope some time to rest. One assignment to work on, but take a rest definitely at some point, and then I'll see you all in the next year.